her nose and eyelid and her ear and her chin. And the old woman, this is her nose and her mouth and her hair. Now, I'm not going to get into the psychology of why you saw an old woman or a young woman.
I'm an old man.
But it's a kind of an optical illusion, and we're going to come back to that in a minute. Let's do another one. Which table's longest? The one on the left or the one on the right? It doesn't matter what you said, but isn't that amazing? I mean, even after you measure it, the illusion still persists. So I've shown you two kinds of optical illusions. One is conceptual, old woman or younger woman. The other one is dimensional or testable. And most of what we've learned, not all, but most of what we've learned in petroleum geoscience in the last 10 or 15, 20 years falls into that second category, things that we can measure. Cognitive bias, in a sense, is analogous to optical illusions. The error remains compelling even if one is fully aware of the reality. Cognitive bias is actually intrinsic to human thought. So, and this is a key point, any system of acquiring knowledge to describe reality needs to have some kind of a mechanism to control for bias. Commonly, we're seeing that such biases result from holding on to deep-seated preferences or even philosophies, and they tend to resist contrary information. And just knowing about common biases doesn't free you, doesn't guarantee that you're free from them. It's important because in our society we depend on science to address and assess issues that affect our well-being. And so it's really important that the science we use for those kinds of decisions should be as objective as possible. It's free from bias. The problem is that we're seeing more and more evidence that cognitive bias is much more common in science and industry than previously realized. And commonly, it's not even accounted for. Now, as I've said when I introduced this, we've learned some things in the exploration production part of geoscience in the petroleum industry that represent an unusual opportunity to gather information and evaluate some methods to deal with this. And so that's what I really want to share with you. In the 20th century especially, science in general achieved a wide respect in Western populations. And many of you may not realize that, but geoscience, geology, geophysics, geochemistry, were not widely used in the petroleum, oil and gas business until after World War II. And when oil and gas companies began to employ geoscientists and professional people in that area, investors began to recognize and to assign more reliability to investments in oil and gas. So the oil and gas industry benefited by having scientists involved in the process. And today, various aspects of geoscience are essential to the petroleum industry. So what do we do, and what are the scientific things that we do, or responsibilities that we take care of as scientists in oil and gas exploration? Well, it's really pretty simple. We look for opportunities, that is, we call them prospects, that is, places where we think there's a high probability that subsurface oil and gas are present. and we try to measure them objectively. And when we measure them objectively, we're striving for two different things. One is, if it's there, what is the size of the petroleum deposit or accumulation that's there, and how, if we produced it, what would be the profitability over time, assuming that it was there. In other words, how much oil, what's it going to cost to drill, what's it going to cost to produce, blah, 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 all that stuff. And then the second is, what's the chance that it is there? And those together, that chance and value, then from a statistical point of view, can be dealt with to generate what we call expected value. It's chance-weighted value, which then we can use as a portfolio of opportunities. And the third responsibility is to communicate objectively with our clients or our investors or our managers as to what are the attributes of this particular opportunity, and recognizing that the company has a lot of opportunities. And it's important that it evaluate those objectively and then pick the ones that are best fitted for a long-term management view. The problem is getting that technical objectivity. We can do good science, good geoscience, good engineering, but when we take that into the business world and we deal with the uncertainty that attends all ventures, the commercial pressures and the self-interest of the people involved, it's always a people problem, it leads, I think you can see why, leads to biased results. And what does that lead to? But for the company, underperforming projects. So the company, the exploration and development arm of the company, does not deliver what it promised. The projects overall don't perform as they were expected to. That's the result. Here's an example. This is from BP's offshore deepwater projects from during the late 1980s and early 1990s. 125 successive ventures. And the red curve shows the volumes of oil that were predicted. So it's a cumulative record of what was predicted to be present in those 125 ventures. The green line shows what actually was found. 45% of what was predicted. And you think about that as an ongoing basis, and you can see a company that is having some problems delivering on its economic performance. Yeah?
When I'm looking at the predicted, the red line, I see flat areas, and that means that there are targets that they predicted no more volume from. Why would they even drill those?
Well, let me see if I can answer that question for you.
Like right below the word predicted, for instance, is a flat area, so that means they're not expecting any more volume from the targets drilled.
Yeah, I think that this thing is actually showing just the volumes of the successful ventures. That's all. Here's another one. This is from ARCO during the 1980s. And I'll explain the graph. The black squares represent the envelope of possibilities for each venture, the central 80% of possibilities. In other words, they were saying for let's say for this project, this would have been the median, that would have been the high side, the P10 value, that would have been the P90, the low value, so this would be an 80% envelope of probability. And the yellow line, and the red is the median for each of those. The yellow dots are what actually happened. Now I'm going to come back to this later, so please try to, hold this one in your mind, because we're going to return to it. Well, what happened is after 22 successful wells, ARCO said, we got a problem. Our geoscientists and engineers somehow are seeing these projects as being much better than they really are. So what are some of the biases that we run into in the business? Well, one of the common ones is confirmation bias, and that bias is when the scientist or engineer already has a sort of a hunch or a predetermined notion of where this ought to be going, and just somehow does not fully evaluate all of the data, evaluates the data that already fit the preconceived notion and sort of undervalues or ignores the data that don't quite fit. Confirmation bias. That happens almost throughout science all the time. People set their predictive ranges too narrow. And one of the ways we test for that with companies is to ask the technical people in your work, do you get a lot of surprises? And when they say, yeah, you say, your ranges are too narrow. There's more uncertainty than you think there is. False analogs, that's where, in almost all of these kinds of projects, we have a kind of an example or an alternative model in mind. This prospect is like this producing field or that producing field. And too often what we find is that the analogs are not analogous, are not adequately analogous. A fourth bias is what we call anchoring, which is that when we start estimating some parameter in some numerical form, that estimating and adjustment process that's supposed to happen does not go to completion, and so the first number biases your final number. And of course the fifth one is the one that is a really serious problem. It's called motivational bias, and that's where the geologist or the engineer says, in effect, I want to get promoted. I can't get promoted unless I find oil. I can't find oil unless I get my wells drilled. Therefore, my objective becomes getting the company to drill my prospects. And it may be good for the geologist or engineer. It's not good for the company because it's not considering the welfare of your employer. And motivational bias applies widely whenever we got folks working on scientific projects. We need to be thinking about what's the self-interest here. So the common causes of these biases are people deciding what the answer is before they should, people believing they have some God-given perception that other people don't have. I used to have an exploration manager who believed he could run his hands over a structure map like a Ouija board and get a sense of whether oil was there or not. I mean, the whole thing was, well, right. Companies that don't have any consistent system for evaluating projects. People that do not have any perspective as to what has happened in the past, either in that basin or in a similar basin, so they don't have a perspective view of things. And the other side of that is people who don't have any imagination. I mean, you know, if we knew everything, we wouldn't have any prospects. If there wasn't any uncertainty, there wouldn't be any drilling opportunities. And so we have to be thinking about what could be, and then when we've identified our opportunity, then we need to measure it. So it's kind of two different acts. People that just are too lazy to do their work thoroughly. Folks who are more interested in their own welfare than they are of their employer's welfare. Management that does not give the technical team time to do an adequate job of evaluating it, either because of time or because of budget. So you force people to be making judgments prematurely. Geoscientists or engineers who don't adequately think about what is at risk here compared with what is the reward here? Okay, and there needs to be an important balance there. Companies that never go back and look at what they did, it's really painful. I mean, I suffered 1,000 deaths with every dry hole I ever drilled. I mean, it really hurts. And if you don't go back and examine rigorously what you said was going to happen and compare it against what did happen, you're not learning. And if you don't learn, you don't improve. And finally, corporations or organizations that have a reward system that rewards activity rather than results. Now, I realize that's harder to do in a public sector science establishment. But the biggest challenge we ran into over years and years was convincing educated technical people, management people, professional people, that they were subject to cognitive bias, just like everybody else is. So I'm going to try to show you some of this. So if you've got some pencil and paper ahead of you, but I am going to ask you to make some predictions, either write them down or put them on a piece of paper. There's one other rule: no joint ventures. Okay. So here's an exercise, and I'm going to give you a kind of a training exercise first to teach you what we're trying to show you, and then we'll do it for real. Okay? How many sheep are there? Now, you're not going to have time to count them all. So you're going to have to estimate. And I think most of you by now have had enough science to know that it's very rare that you get the exact number. You get some number or range of numbers that approximates the correct answer. Now, you're going to have to estimate, because I'm not going to give you enough time. Okay? So before we do that, let me suggest a way to do that maybe you may not be familiar with. And that is, instead of estimating as a single number, I want you to estimate as a probabilistic range. And the way you do that is to pick a low number so that you feel like, well, I'm practically certain, about 90% certain there's more sheep than that low number. And then pick a high number such that you think, you know, there's only a small chance there's more sheep than that, maybe a 10% chance. So you're sort of thinking in terms of an 80% range, okay? So I'm going to ask you to estimate sheep with a range, and that range, conceptually at least, represents 80% confidence. Everybody understand what I'm saying? Is that clear? One or two of you are looking at me like a bull studying a new gate.
But you've introduced an unfair variable in the fact that we had so little time to look at it.
Well, I'll give you another shot at it. I just wanted to get your attention.
But if you're looking at an oil, we have plenty of time to look at the data.
Yeah, you do. But what you find is a certain irreducible uncertainty. But that's okay. I wanted to show you how to, if you haven't tried this, it's kind of an interesting way to estimate. So your P90 is a low number, there's more sheep than that. And the P10 is the high number, and there's only a small chance of more sheep than that. And the range represents 80% confidence. Okay? Don't forget these one getting off here to the left.
That give Al enough time?
I don't know.
I was trying.
You're just learning. How many of you had a range that included the number 175? Hold your hand up. That's pretty good. That's about 60% of you. Yeah. Yeah, that's not bad. Not bad. Okay. Now we're ready to take this seriously. Okay? How many beans are there?
A lot.
A lot. Okay. I want you to do the same thing with the beans that we did before. So now we're talking number of beans. Let's talk about it here a little among ourselves. So suppose this is a log probability graph, just to show you. This is a probit scale here. So this is 50%, and it graduates outward symmetrically. And this is a log scale. So it's, and a straight line on a log probability graph, by definition, is a log normal curve. Now I'm going to give you a big hint. Estimates of beans distribute log normally. Now, the math of log normal is that if it's a multiplicative process, the final outcome is distributed log normally. So what's multiplicative about beans? Height times width times density. And your eye is doing it naturally. So if we figure it's going to plot, if we know it's log normal, and we force the distribution estimates to be log normal, guess what? You make better estimates. That's something we learn in our business. Okay, so you think there's more than 10 beans there? Yeah. You think there could be more than 100 beans there? Yeah. Okay. How about the high side? You think there's 1,000 beans there? Don't know. Okay, can you see automatically that we're now generating a line, a slope? See what I'm saying? Okay. Okay, let's estimate beans. So everybody got your low number? Everybody got your high number? Don't look at your neighbor, because that'd be the blind leading the blind. Well, so hold your hands up again. I'm trying to figure out how many people you think are in this room. About 60? Think so? That many?
Well, they're more than 10, but they're less than
Could we get somebody to count the people in the room? For the point of the discussion, I'm going to estimate that there's 60 people in here. Okay.
Is that your P10 or your P9?
That's a seat of the pants. A WAG. Okay. You know WAG? The first word's wild and the last word's guess. Okay. So, again, if your range included 1780, hold your hands up. 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 60. Is that 80%? That's about 15% maybe? Huh? 13%. So we asked you to estimate at 80%. Here's the payoff. We asked you to estimate at 80% confidence. And you estimated as a group at 13% confidence. So as a group, you're biased. I mean, you're not bad people. Now, some of you are doubting Thomases who say, couldn't possibly be 1780 beans. How many of you are doubting Thomases? Well, before I do that, let me ask you. So this number's about 13%. So you're overconfident as a group. You're overconfident. Your ranges are too narrow. Should have set wider ranges. Now, are you conservative or optimistic? How many of you had a range entirely below 1780? Hold your hands up. That's okay. So you were conservative. Another bias. Okay, as a group. That's the message. Estimating bias is endemic. It happens all the time, even if you know about it. Now, for those of you who don't think there's 1,780 beans there, that's 209. Are you satisfied that 1,780 is not a bad number? Thank you. So let's look at these ventures that we develop and drill, spend lots of money drilling. There's a lot of uncertainty about the reservoir quality and about the area of the accumulation and how thick it is and all that kind of stuff. We can use seismic and modern technology, and it reduces uncertainty and it clarifies it, but it doesn't eliminate it, not even close. Still a lot of uncertainty. The prospecting process itself leads to advocacy. The fact that it's science, quote unquote, reinforces the apparent confidence of the management. And finally, it's hard to see each prospect as part of a series of prospects. Instead, we tend to, because we've worked on it, we've sweated blood over it, we tend to see it as a one-off deal. And so it's hard to see that perspective. And of course, nobody likes to bring bad news. They kill the messenger. Well, if we look back at the history of the oil and gas business in the United States at least, early on it was recognized that this problem existed. So what could we do about it? Well, we set up the SEC, which established definitions of proved reserves. And that proved reserves number formed a basis for establishing the value of the company for investment purposes. States began to license engineers or geoscientists, trying to weed out the incompetent ones. Companies would bring in outside experts to review projects to bring an alternative view. Some companies took the position that engineers by their very nature were conservative, and geologists or geophysicists or whatever, anything with a geo in front of it was a blind optimist. Okay, well, it wasn't fair to either discipline. Set up lots of negative stuff between the disciplines. Some executives would just use their own personal rules of thumb, which were often wrong, counterproductive, and all that sort of thing. And of course, with projects in different parts of the company, different executives, then that contributed to the lack of consistency. But in the industry overall, over time, people working in the industry kind of knew what operators were responsible and dependable and straightforward, and those that were fly-by-nights. So over time, there was a way we sort of sorted some of that stuff out. It was not very effective, but some things worked. And of course, the threat of lawsuits and public exposure served as something of a break. The problem with those methods was that the underlying causes and the remedies of the bias were not being addressed. It was like a Band-Aid on a bleeding sore. So we learned some things over 20 years, really looking hard at this issue of bias in our geotechnical work. And this is where it begins to start spilling over into your field, whatever field of science you're in. Number one is whenever we had the provisional parameters of a project, we would perform what we call plausibility checks or reality checks. And I'll show you an example of that in a little while. We urged people to deliberately try to ascribe an opportunity to explain it, to deliberately search for other alternatives. What else could this be, as a way of trying to widen our ranges? We went to probabilistic estimating, because if you start keeping records, after a while you find you can begin to measure your ability to make these judgments under uncertainty. It's a learning process. We noticed that most E&P parameters did not fit the bell-shaped curve. They fit the log normal curve. That's the sharp peak to the left, or for you guys this way. I have to draw backwards that way. Okay. We found ways to utilize independent judgments, knowledgeable people giving their subjective opinion, sort of drawing on the idea of the Delphi round method of dealing with uncertainty. And we began to manage E&P not as a one-off project, but as a portfolio of opportunities. So we were thinking of then an annual portfolio the way you might think of after an evening at the gambling casino when you're playing roulette. Now, you don't know what the odds are going to be. You don't know what the outcome on any one trial of the spin of the wheel. But the house knows what the odds are on that wheel, and they are set slightly to be in the house's favor. So given 100 trials or 200 trials, you can say probabilistically what the result ought to be. And that's basically what large companies do now. And then probably the single most important thing we learned to do was to do careful performance tracking of ventures. So we began to measure our abilities to estimate. And there's a wonderful article that was published by Exxon people in the either January or February AAPG bulletin by Exxon that actually recorded 20 years of this stuff. And it was remarkable. By now, they do it pretty well. Okay, let me give you an example of a reality check. Now, let me start by explaining the graph. This is a log probability graph. Here's the P50 and P90, P99, P10, P1 log scale. That's a graph of all the oil fields in the world as of about 1985. Okay, and the red line is the plot, mathematical fit. The blue line represents all these fields, and they've plotted I think every 100th field. Okay. So the P50 for all the oil fields in the world as of that time is 5.4 million barrels, ultimate recovery. The P90 was 250,000. The P10 was 143 million. The P99, that's really sobering, 18,000 barrels. 1%, the smallest 1% of all the oil fields in the world are 18,000 barrels or less. And that's a non-commercial, clearly a non-commercial well. Okay. Okay, now what do we do with that? All right. Same kind of a graph. Here this is for an individual project. That's 10,000 barrels, 100,000 barrels, a million, 10 million, 100 million, a billion. Now, is it clear that the slope of the line is an expression of the uncertainty? If this line was vertical, there's no uncertainty. We know exactly how big it is if it's there. Is that clear what I'm saying? No, it's not. Okay. Let me try you again. If the slope of the line is vertical, we're saying there is no uncertainty about how much is in that opportunity. Hello, come in, Cairo. All right. Okay. Now, does it also follow that if it's vertical, there's no uncertainty? Then is it also clear that as this slope increases, there's more and more uncertainty? Is that clear? Okay. Let me give you one more hypothetical. Think about what we learn in developing an oil field. We drill the first well, a lot of uncertainty. As we drill the development wells, individual development wells, each one has less and less uncertainty. So is it clear to you then that if we think about the exploration well versus the development well, which is drilling within the field, is it clear that the development well should have less uncertainty than the exploration well? Okay, now let me tell you what we find time and again. We go in, we look at an exploration project, and here's the project, and it says, well, here's the reserves distribution given discovery. With 15 million barrels, 25 million barrels, and with a P10 and 3 or 4 million barrels. And so we say to the team, what you're telling me is, given discovery, there's a 1% chance of 2 million barrels. Is there any possibility that we drill this well, we find 500,000 barrels? 100,000 barrels, 50,000 barrels. And at some point they'll say, yeah, it could turn out to be a crummy little one well field. And we say, how come your blue line doesn't come down here then? That's a reality check. And what typically happens as soon as this line starts coming down in that area, our forecast of what the reserves will be given discovery improves very substantially. Because what we're seeing is when they're estimating the possible reserves in the project, it's not that their high side is too high, it's that their low side is too high. And as a result, the slope of that line, which they show as this, should be like that. That's one of the things we learned. As ways of sort of look at an early stage, looking at their work and identifying bias. Multiple working hypothesis comes from T.C. Chamberlain back before the turn of the 20th century. It was published again by Journal of Geology in 1931, but the original work was published in 1895. And Chamberlain was talking about the deliberate setting up of alternate hypotheses to explain the opportunity or explain the situation. It's a way of widening your ranges and bringing discipline to your investigation. And there's some practical ways to do that in our business. What else could this be? Make more than one map, so that we're deliberately trying to push our envelopes. Estimating the probabilistic ranges, you're now expert at that. Many of you remember the childhood fable about the 6 blind men from Hindustan who were describing the elephant. Does anybody remember that? And the guy at the front said the elephant was like a giant snake or a curved spear or a fan or a leather wall or a tree or a bell rope. Individually, they had it all wrong. Collectively, they had it about right. So if we can figure out a way to get knowledgeable people to make independent, informed estimates and then begin to average those estimates, we get much better estimates. The problem is keeping their estimates from being influenced by other people. Well, you know, you're entitled to, at this point in the game, to say, well, that's all very interesting stuff, but does this work? Well, let me tell you an interesting story. Mobil Oil Company in about 1995 was in the process of adopting these kinds of systematic processes. And of the 54 projects, exploration projects, the discoveries that were made that year, of those discoveries, 26 of them had been generated using the guidelines, and 28 of them had been generated using previous guidelines. And notice, first of all, that the outcomes were distributed approximately evenly among the 20th of each centile, each 20%. Actually, they were a little conservative because there were a few projects that clearly came out better than they had estimated. And the group that had not estimated using the guidelines, half their projects fell in this lower 20th percentile. So this is an example that shows you pretty clearly that this stuff really works. And that's why it's been mostly adopted by most of the industry by now. Okay, back to cognitive bias. The sort of recognized authority on this is Daniel Kahneman, wrote a book called Thinking Fast and Slow. How many of you read it? Read it. It's a really good book. Really interesting. And Kahneman and his co-worker, Amos Tversky, who's passed away, I don't know, 15, 20 years ago, together they won the Nobel Prize in economics, because this is the interface of psychology and economics. He said there's two ways of thinking. System fast, or system one, which is thinking fast, uses association and metaphor to produce a quick and dirty draft of reality. System two is slow thinking, thinks deliberately and rationally, arriving at reasoned choices. The problem is that system two tires easily and often accepts the unreliable story about the world that system one feeds it. Some of you who are philosophers may wonder if this all goes back to Plato and Aristotle. Aristotle was the slow thinker, Plato was the fast thinker. But it goes back to what I was talking about, optical illusions. Conceptual is fast thinking stuff. Dimensional or testable is slow thinking stuff. System one operates automatically, quickly, little or no effort. It's an intuitive process. It's associated with fight or flight. System two uses controlled and conscious mental activity. Critical, deductive, logical thinking requires deliberate effort. System one is the older part of our brains in an evolutionary term, tends to receive information first before system two does. It's more prone to error in complex or uncertain situations. But you know, we can't, if we try to apply system two to everything, it's paralysis by analysis. So, you know, we have to sort of judge when we need to use system two. Our problem is that we tend to use system one because we're lazy. System two is the more recent part of our brains, evolved to manage uncertain situations. I used to have a colleague who's gone over the Great Divide, rest his soul. He said, people will go to almost any length to avoid thinking. Well, he was talking about system two, wasn't he? So we have methods. I've shown you methods for coping with part of the problem of cognitive bias, the testable system two part. The problem still remains the conceptual or system one bias problem. So how do we deal with that constructively? I mean, for example, it doesn't do anybody any good for me to say, Gene, you're a lot more biased than I am. I mean, that sets up all kinds of negative stuff. I mean, for example, your parents probably told you at some point, son or daughter, don't argue politics and religion in public. Right? Anybody get advice like that? Get you in trouble every time. Well, why? Well, because stuff like politics and religion is kind of deep-seated psychological, social stuff, not amenable to analysis in a mathematical context. So how do you, we all had experiences where we had a confrontation with somebody on an issue that really there was no way to logically analyze. So how do you deal with that? And the solution, as Jonathan Haidt says, who wrote a book called I'll think of the name of it. Anyway, he said, maintain your respect and communication with the individuals. Number two, focus on process and decisions, not on the subjective argumentative stuff. And finally, at some point after the project has been done, after the results are in, then go back and look and say, okay, you said this, I said that, opinion, blah, blah, blah. Here's what happened. And it gives you then a basis for beginning to have some productive interface. But there's more to this. Emily Cronin, Princeton, 2004, published a paper called Objectivity in the Eye of the Beholder, Divergent Perceptions of Bias in Self versus Others. She says, people see themselves differently from how they see others. People are immersed in their own sensations and hard work and emotion and cognitions. At the same time, they can only judge the same sort of thing in other people. So immediately there's an asymmetry. And it leads to, lots of times, conflicts and arguments and one thing and another. So understanding that, then I think begins to put you in a situation of trying to ask people, where are you coming from? questions like that that begin to open things up and begin to allow some interplay and exchange of bases. Now, I'm going to give you an example of this, and I'm not going to embarrass you by asking for your opinion, but I am going to go back to 3 different, basically scientific issues that have now become topics of public discourse and public controversy. And so I'm going to ask you. I'm not going to ask anybody to give their opinion. In fact, I don't want you to say anything out loud. I just want you to think about this. Genetically modified foods are too dangerous. You agree with that? Don't know? Disagree? Vaccinating kids is too dangerous. You agree with that? Don't know? Disagree? Man-made global climate change is too dangerous. Do you agree with that? Don't know? Disagree? If you think other people's answers to those questions could show bias, do you think yours could too? What are the sources of your information about these things? Many and diverse, few and uniform? So why is all this important? Most scientists recognize the existence and operation of cognitive bias much more in other scientists than they do in themselves. Private sector scientists, because they are profit-driven, often have ways and motivations to cope because at the end of the day, they're being judged on results. Public sector scientists recognize the existence of cognitive bias in scientific work theoretically, but very few of them produce active measures to control it in their own work. And I'll pose the question, I don't have an answer for it, but I'll pose the question, is this an accountability issue? Here's just a couple of insights from a paper that was written by Kahneman and his chief opponent, a guy named Klein, who thought that intuition was really very powerful, and Kahneman was saying, no, system 2 is the powerful one. But they agreed that the confidence people have in their intuitions is not a reliable guide to their validity. So then they asked the question, well, in what kind of situations is it that your intuition does become reliable? One is a predictive environment that is relatively regular and repetitive, like weather forecasting. Or when there are opportunities available to learn those regularities through practice. It's been identified that the most skilled scientists dealing with uncertainty are weather forecasters. And the reason is they got lots of practice in predicting what's going to happen and seeing what happened and improving. Repeated trials. So when are intuitive decisions inappropriate? When are they appropriate? And that is where time and danger don't allow objective analysis. The basic problem comes when we are using System 1 to make decisions when circumstances permit the use of System 2. That's what the fundamental problem is. That's where the laziness comes in. Richard Feynman, one of my heroes, said, the first principle is that you must not fool yourself, and you are the easiest person to fool. He said, dedicated practice of the scientific method is key. A kind of scientific integrity, a principle of scientific thought that corresponds to a kind of utter honesty, a kind of leaning over backwards to try and prove your theory wrong. Well, I haven't talked much about about motivational bias in here. It's mostly been other forms of it. But Mark Twain made a comment about weather. He said everybody talks about it, but nobody does anything about it. And I think that the American scientific community, not just the American, the Western scientific community, does talk about it, but people that actually practice methods of trying to detect it and correct it are pretty rare. So the fact is, though, that as I've shown you, that many geoscientists and engineers who work in our industry do so routinely. They have to. And the problem is, how do you transfer that kind of experience into science as a whole? That's one of the reasons I'm here. I haven't said much about motivational bias, but here's a couple of examples that are knowledgeable people who gave what was represented as an authoritative opinion. Harry Warner in 1927, he said, "Who wants to hear actors talk?" You think Harry Warner had any interest in whether you used talking pictures or silent pictures? Darryl Zanuck said in 1946, he was a movie producer, he said, "Television won't last because people will soon get tired of staring at a plywood box every night." You think Darryl Zanuck had any skin in the game? Sure, he was being motivated by his own interests, maybe not consciously, but my favorite is this one from Thomas Edison. "Fooling around with alternating current's just a waste of time. Nobody would use it ever." And he was trying to get the whole country to go to direct current, you may recall. In my business, petroleum geoscience, motivational bias was a selective use of data that overstate the expected value of a project in which the geoscientist perceives personal benefit in getting the company to drill. In public sector science, selective use of data that support findings that are more likely to attract funding or to promote favored personal socio-political philosophies. Both are conflicts of interest. Both are unprofessional. We see a lot of this going on today, those of you who are sensitive to it, at USGS, a mass spectrometry lab that was investigated twice by the Inspector General. And they were basically generating results tailored to whatever the scientific investigator wanted. And the result of it, it turned out 24 research projects totaling cost a total of $124 million were compromised. Several of them had to do with looking at freshwater, surface freshwater analysis in public lands east of the Grand Canyon, not in the Grand Canyon. And the BLM was interested in having a public moratorium on surface mining, even exploration for public mining. Now that may or may not be a good idea, but it turns out the data on which the decision was made were fraudulent. Today, more and more we're seeing authoritative papers, articles, basically questioning the authenticity of research findings. Nature in 2012 said 47 of 53 published results of cancer research papers were irreproducible. 80 to 90% of claims from scientific studies in major journals failed to replicate. From Science in 2015, 39% of published psychological research could not be reproduced. Richard Horton, this is a recent one in The Lancet in 2016. The case against science is straightforward. Much of the current scientific literature, perhaps half, may simply be untrue. Now this is a responsible, technical question.
If I may. 80 to 90% of claims from scientific studies in major journals fail to replicate. So how many journals would you think comprise major journals there?
Well, I could make a guess at it.
The reason I ask the question is I just find that, I read that.
Yeah.
Major journals. I mean, there's hundreds and hundreds of journals that are out there.
Depends on your definition.
Okay, so let's say there's 100 major journals, right? And so then how many articles are in each one of those journals? And then extrapolate that over some period of time here that's not mentioned.
I agree.
You're going to say that 90%, let's take the meat of the middle. 85% of those were not able to be reproduced. I don't believe for a second, now maybe this is just bias, but I don't believe for a second that somebody has set out, or multiple people have set out and done that work, picked up those journals, and we're talking about thousands of experiments at this point in time, conservatively speaking.
I'll have to go back and read the article.
But you see
I'll
what
take
I'm
you,
getting
certainly,
at.
certainly.
I heard these kinds of things,
I
and
think
I
it's a,
just say to myself, and I don't doubt this.
Yeah,
I'm in the private sector. I work in oil and gas, so
yeah.
I'm with you on this. I'm not a doubter on what you're saying.
Sure.
I read these kinds of things, and I just find that number, it just strikes me as almost ridiculous.
off the wall.
Off the wall.
Yeah.
What's it based on?
I hear that.
You nailed it, though.
I hear that. But
What that quote is saying is that all the studies they didn't replicate the studies in the journals, and 90% of those studies weren't replicated. Not that they couldn't be replicated, but that they weren't.
Is that the statement? Because those are two very different statements. If he's correct, then
I think you're right, John, that's what
That
that
makes more
article is
sense.
about.
yeah.
yeah, I think that's a good distinction. Thank you for making it. Yeah. But even so, I would say it's an extraordinarily high number.
Yeah. I mean, the question I would ask, we have a room full of scientists who some of, Gene, I don't know how many publications Gene has. I mean, Gene, how many times have you been contacted to have somebody tell you, hey, we tried to replicate your results and they were no good? And of all the scientists here, how many times has that happened to you? Anybody?
No.
So maybe John's correct, I think that was John, in saying that it's just that nobody tries to replicate it, not that they can't be replicated.
There is a current website called Retraction Watch, which I visit every once in a while. And the number of formally retracted papers is going up very steeply.
I don't doubt that.
And that I think is what we should focus on. Yes, ma'am.
Do you think though that yeah, I mean proportionally are they going up, but also I think there's fewer people looking at the paper, or more people looking at the papers and critically looking at the papers than there
Could be.
were 50 years ago.
You could take that statistic as a positive sign that science is finally beginning to clean its act up. You could do that.
Yeah, I mean I find it hard to believe that there's more bad science now than in the past. But
Well,
there's also a lot more
let me pose a thought for you to think about, okay? For folks working in the public sector, working on grants and one thing or another, you're not being paid to publish a paper which is correct. You're being paid to publish a paper. And so although the scientific review process may work, we all know it works slowly. And so there may be a time effect here, because let's face it, the number of papers being sponsored by public money over the last 40 or 50 years has done that. So I'm willing to say, well, maybe we're looking at something on a time series that hadn't played out yet.
Another thing, just last thing, is if either way you look at it, what it tells me is most of what's being published is useless. Because the world moves on. Technology advances faster than we ever thought it would. We find more oil every day. All these things, buildings, they stand, they get better, technology, all these things. So if the science is bad, it doesn't seem to be having much of an effect on the world. Life expectancies have gone up, all these things. So it tells me, and I sort of believe this, that most of what's published in journals, true or not, is more or less irrelevant.
But also, I think there's a real question of what the word untrue means in science, because in science, a lot of the results is we're getting closer to an answer. We're not necessarily saying, here's exactly how it works, here's how we think it works, and we progressively get towards learning how things work. So this idea of it simply being untrue, I'm not sure that actually fits with how science works. So
There's got to be a lot of cognitive bias in replication. I mean,
Well,
you set
if-
out to prove somebody wrong, you're going to prove them wrong.
yeah.
Well, that's why we're supposed to provide all our information as to how we did the experiment, isn't it? This is, I think, maybe this is more prevalent in some parts of science than others, but I thought this was really, really attention grabbing. Richard Smith was editor of the British Medical Journal for 13 years, and he said research misconduct degrades trust in science should be a crime akin to fraud. That's a pretty strong statement. I wouldn't go that far. But he said, after 30 years of observing how science deals with a problem, I've sadly come to the conclusion it should be a crime for 3 reasons. First, some people have been given substantial grants to do research, so it's really no different from financial fraud. Secondly, we have a whole criminal justice system that's in the business of gathering and weighing evidence, which universities are not very good at. And finally, science itself has failed to deal adequately with research misconduct. That really got my attention. Philip Handler said, scientists best serve public policy by living within the ethics of science, not those of politics. If the scientific community will not unfrock the charlatans, public will not discern the difference. Science and the nation will suffer. Okay, this is a graph that I find very interesting. It's a graph showing the projections of about 40 some odd computer programs for sort of average global warming projected out to 2020. That's one standard deviation. That's the mean of all those. This is the University of East Anglia surface records, and this is atmospheric warming, one from weather balloons and one from satellites. Now, you look at that diagram, and I think you have to say something wrong with the modeling. By analogy, we showed you this diagram from ARCO. ARCO looked at that, we're doing something wrong. Now, I don't know what it is. It's out of my field. But just objectively looking at this, I think you have to say something wrong with modeling. So it leads us to it seems to me, it leads us to the question about what is the proper role for scientists in our public dialogue. And I'm going to provoke you by saying that a scientist working in marine science should not be an advocate for funding in that area. I'm saying that if you're an advocate in your own research area, you're no longer objective. Somebody want to take me on about that? I'm just asking you to think about that. I'd love to see you being politically active in some other area, but not in your own field, not politically or
Well, by that side, should the oil companies be politically active against climate change? That's kind of something that they're related to in a business venture, or should they stay out of it as well?
Well,
It goes both ways.
I agree with that. I agree with that. I guess I would respond by saying, first of all, I'm not politically active with regard to climate change. Okay, but I'm not a climatologist, but I am a scientist. And when I look at that diagram, as a scientist, I'm saying there's something wrong with the modeling. I don't know what it is.
I can show you a diagram showing the surface temperatures and the models that agrees very well. So I'm not exactly sure how they were calculated.
Sure.
Well, one thing is wrong with the diagram, it stops in 2011, right? And there's been significant warming since then.
I heard on the news this morning that the Germans are growing a third of their grapes now are red grapes, or for red wine grapes,
Yeah.
and as opposed to white
Yeah.
wine. And 30 years ago, they couldn't raise
Yep,
any red
I
wine
agree.
grapes.
I agree.
So, and my plumeria tree
Sure.
blooms in March
Sure.
now, as opposed to when I first came
Yeah.
to Florida, it bloomed in May.
The argument isn't has it been getting warmer? That's not the argument. I agree with it. It's been getting warmer. But it strikes me that if someone's trying to model it and you look at empirically at the data,
Well, so what's in that graph? You have a lot of solid of lines which fall within the range of the real data, and then you have the lines with the points. What's the difference between the lines that don't have the individual data points?
Those are models, and I'm presuming that it plots those projections as continuous projections, but I don't know. It's not my graph.
Yeah.
All I'm trying to do is to show you two what look to me like analogs, analogous situations, and we know what worked in the second one. Yeah.
This is, I applaud you for showing us the numbers on the x-axis.
Yeah.
Because I've seen this plot numerous times without numbers on the x-axis, so somebody can't say it only goes up to 2010,
Yeah.
2011,
Yeah.
right? You had the recent years, and you have some really big spikes in temperature.
Sure.
The other thing is the sea level curve. We have the same forecast for increasing sea level. Those numbers actually, with the observations plot on the top of the envelope there, so you could argue that modelers have been too conservative in that case.
Could be. Could be. And I'm not, I'm just looking at the numbers, looking at the data, and so, what do you conclude from that? Okay, let me wind this up. We've already shown you that because exploration is dominated by uncertainty and there's self-interest involved, we see commonly that our people tend to overvalue the projects, the prospects. And so then it asks you to think about, well, what are the professional responsibilities of petroleum geoscience? And I would argue there are two. One of them is to find these opportunities. That's the fun part. And the second one is a different process. It's measuring them. And that's the business part. And I would almost argue that you either have to have a remarkable sense of detachment, or you need to have a separate team review the data and make an independent judgment who don't have skin in the game of that project. So I like to think about it being done by the same people because I like a holistic approach to things. But it takes you to a kind of a yin-yang concept about the business. And it says we got really two parts of our business. One is the vision and intuition that goes with identifying opportunities, and then the second one is measuring them. But it requires detachment. But the basic message, how to reduce cognitive bias in science, goes back to Feynman's comment, a renewed commitment to the rigor of the scientific method. Thank you for your attention. I'll be happy to take any comments. Yes, sir. Yes, ma'am.
We've been discussing cognitive